Hi there, you are watching a video of shell and tube heat exchangers for industrial plants. The code does not recommend or suggest any material for any particular application. The code merely states what materials are allowed and the requirements they have to comply with. There are materials resistant to almost all fluids. The problem is the cost of these materials. The selection of a material is a compromise between corrosion, erosion, fluid contamination and cost. The material selection is always a technical economical solution. To select a material for an application, the following should be consulted: best practices and lessons learned, authors of reference, current publications like API or NACE, client specifications, and metallurgy specialists. The lifetime of an equipment in different industries is often reduced as a result of corrosion, reason for which special attention has been given to this study. Achieving significant results with respect to detection and control of corrosion is key. In technical terms, corrosion is defined as the deterioration or destruction of a metallic material caused by electrochemical attack from the surrounding environment. In practical terms, it is almost impossible to eliminate corrosion. The effective engineering work in this field is more towards controlling it than completely eliminating it. Uniform or general corrosion acts evenly on a metal surface, which in most cases can be controlled, providing a range of admissible corrosion thickness. The metal thickness will wear off uniformly over time, which is the most common and least dangerous from all types of corrosion. The contact of metals with different electronegativity produces significant corrosion rates when the fluid is of electrolytic nature. An electric discharge is caused between the metals, also known as galvanic corrosion. When the corrosive attack is generated on a metallic surface due to the flow velocity and producing mechanical wear, this is called erosion. Selected materials must withstand the effects of corrosion and must be strong enough to withstand design pressures and temperature, at the same time arriving to a practical design. In order to select an adequate material for a concrete application, the following properties shall be evaluated: allowable stress, corrosion resistance, temperature resistance, and toughness or resilience. First of all, the main mechanical properties of steel must be known. The basic mechanical properties of steel can be obtained through a typical stress-strain test. The diagram shows point A is known as yield point. If the tension load is released at any point below point A, the material returns to its initial state without any permanent deformation. When this point is exceeded, the material is no longer elastic. Releasing the load on this range leaves the specimen with the permanent or plastic deformation. Point B is known as tensile stress, and point C is known as rupture point. Interestingly enough, none of the aforementioned points is used for the design of storage tanks. So, what is the allowable stress to be considered in our designs? Pressure vessels, among other mechanical equipment, must not work within the plastic deformation zone under any circumstances. After point A, the material has lost its initial mechanical properties permanently. Therefore, the allowable stress is always a percentage below the yield point. This percentage is the safety factor, and it defines the allowable stress. The allowable stress is established by the design code for each case, and it is selected for a given material and the design temperature. Allowable stresses for all accepted materials to be used in the design of pressure vessels according to Section 8, Division 1 are found in Table 1A of Section 2, Part D of the Boiler and Pressure Vessel Code. Depending on the design temperatures of an equipment, a particular material will be selected. The selected material will be able to withstand the maximum temperatures prevailing in the process. As a general rule, materials are used in the following temperature ranges. Up to 350 degrees, carbon steel. Up to 650 degrees, chromium molybdenum alloys. And to prevent corrosion, high alloy steels, or most commonly known as stainless steels. In addition to the ranges previously described, there are guides such as the one shown on the screen, taken from the Dennis Moss Pressure Vessel Design Book, which recommends materials for different working temperatures. Brittle fracture occur due to fragilization of the material structure. They can be visualized as a piece of glass breaking into the floor, exaggerating to keep it simple. This type of failure occurs at low temperature, generally below the design temperature. The most dangerous of such failures is that they take place without any warnings and the consequences are catastrophic. To verify that a material has the adequate toughness, the MDMT of the material must be compared with the minimum temperature required by the process or environment. Let's remember that the MDMT is the minimum design metal temperature. In the event that the material does not meet the above-mentioned requirements, that is, that the MDMT of the material is higher than the required by the project, an impact test, commonly known as CHARPY, can be carried out to determine the exact properties of the chosen material. The MDMT is determined as per the indicated in section UCS 66 of the ASME code. This section presents characteristic curves for each material, where the curves indicate the minimum metal design temperature MDMT depending on the material and the thickness of the component. These curves have been obtained through tests and equipment experiences operating satisfactorily. Let's see this with an example. It is necessary to determine if the material selected for a new vertical pressure vessel is suitable to operate at the minimum working temperature of the project. The data of the pressure vessel is the following. We are talking about a vertical pressure vessel in the new condition, where the minimum temperature of the environment, or CET, critical environment temperature, is minus 19 Celsius degrees, where the shell is presenting a thickness of 25 millimeters and a material that is SA516 grade 70. For heads, the thickness is 13 millimeters and the material is SA516 grade 70 as well. Let's bear in mind that these materials are in the non-normalized condition, at least these materials have been specified in the non-normalized condition. Let's see what happens with this case. Since the materials are non-normalized, curve V, as per the indicated in UCS 66, should be used. So for the case of the heads, 13 millimeters thickness, and we are going to cross curve V, we obtain minus 20 Celsius degrees of MDMT. Since the MDMT is, let's say, lesser than the project temperature, the material is apt. It doesn't require any further investigation. Let's see what happens with the shell. In this case, entering with the shell thickness and crossing curve B, we obtain MDMT of minus 0.5 Celsius degrees. In this case, the MDMT is higher than the project temperature. So, in this situation, the material is not apt, and it does require further investigation. In other words, Charpy test. It should be noted that to determine the MDMT of a pressure vessel, it is necessary to obtain the value of each of the components, later determining the overall value of the equipment with the most restrictive of all the elements or components. One aspect that is essential to know is the designation of the materials that can be used in the manufacture of this type of equipment. The biggest challenge with the ASTM or ASME designation lies in the fact that even when the metallurgy is the same for the whole vessel, carbon steel for example, components may have different designations depending on their fabrication method: casted, forged, welded, etc. For example, for carbon steel metallurgy, a pipe may be A106 grade B, while a flange would be A105, and so on and so forth. Line materials. In order to protect the base metal from corrosive attack, it's very common to use combined or hybrid solutions. This means lining the pressure vessel internally with a material resistant to such corrosive attacks. The internal lining can be achieved in two ways: by means of internal cladding or by means of a weld overlay. Cladding consists of joining two sheets: the base material, pressure resistant, on the outside and the corrosion resistant material on the inside, welded or fused through different methods. In turn, the weld overlay consists of welding a corrosion-resistant material to the base material, resulting in a protective layer.